Okay, thank you. Thank you for coming this late in the conference. Okay, so I'll be talking about this problem. You want to optimize a quadratic form over the Hamming hypercube. And well, this is hard to approximate within a polylog factor. And by Grothendieck inequality, one can get order log n approximation. But I will not be talking about any of these. I'll be talking about random instances. Why I'm interested in random instances? I'm interested because of problems from statistics or machine learning. Simple example is the stochastic block model. In the stochastic block model, you generate a graph by first generating labels, IID, uniformly random in 1 to k, where k is some fixed small alphabet, and then you lay down edges independently with probability p if the two vertices have the same label, and with probability q otherwise. And then you are given a realization of the graph, and you want to estimate the labels. If you write down the maximum likelihood estimator, that is kind of the most standard statistics estimator, it boils down to maximizing some sort of quadratic form over the graph G, or equivalently over the matrix A, that is the adjacency matrix of the graph. So the problem k equal 2 is exactly the problem that I'm trying to solve with A, the adjacency matrix of a random graph. Now, this problem is well understood where P and Q are very well separated, where the signal is very strong, so somehow there is a unique global optimum that is much better than all the rest. But I'm interested here in the opposite regime in which there is not a strong signal and data is very noisy. So possibly there is many optima that are equally good, or more than one optimum that is equally good, or roughly equally good. So the simplest model in this class is this, that is the Sherrington-Kirkpatrick model, and it's just a specific distribution over matrices A. I'll take A to be a symmetric matrix with entries above the diagonal to be independent, not necessarily IID. And mean 0, okay, the variance is just a matter of scaling. I set it to be 1 over n, and I assume them to be C over n sub Gaussian. Okay, so they are of order, entries are of order 1 over square root of n, 0 mean, and they have good tails. So this was introduced in physics by Sherrington-Kirkpatrick in 1975, and it's really a prototype of a large family of random combinatorial problems. If you were here for the previous talk about not all equal SAT, that comes out of the same line of research that started more than 40 years ago. And the ideas that were used to solve this problem were then used to solve random k-SAT and so on, to solve typical properties. And there is a fascinating problem, algorithmic question. Here, these have been studied in physics and in probability theory for 40 years. There is a fundamental computational question is which of these optimization problems can be solved in polytime. All right, this is just a cut and paste of the paper of Sherrington-Kirkpatrick, and this is the definition of the model. Basically, it's the same that I gave just now. So what did we know before this paper? Well, the problem is not obvious to solve. For instance, we know or we expect there to be exponential number of local maxima. We know the asymptotic value of the optimum. If you scale it by 1 over n, this converges to a constant that is about 0.763. This was conjectured, obtained non-rigorously by Parisi in 79 and proved by Talleyrand in 2006. You can then try convex relaxations. If you do the spectral relaxation, you get that the value of the spectral relaxation converges to 1. So it's wrong by a factor 25%. You say, okay, I'll try SDP. You do SDP, and SDP also converges to 1, so it doesn't get you anything better than the spectral relaxation. This we proved a couple of years ago. It's not difficult. After this paper was posted, was out, a couple of groups looked at it from the point of view of SOS4 and obtained that even SOS4 converges to 1. So SOS4 is no better than spectral. Okay? Natural conjecture is, of course, that all constant level in the hierarchy fail. Of course, SOS is trying to solve a more difficult problem. Okay, so what is the theorem here? There is an assumption, no overlap gap. It's a technical assumption that I'll explain in 5 minutes. But under this assumption, for any epsilon, there exists an algorithm with complexity Cn square that outputs a solution, a feasible point, which is 1 minus epsilon of opt. Okay, does the theorem make sense? Okay, great. So if you don't like random matrices, you like random graphs, you can apply this to computing cuts of random graphs, right? So both max cut and minimum bisection can be formulated with a little bit massaging in this framework. What is the typical value of max cut and min bisection? Well, it's the value of a random on an Erdos-Renyi random graph, NP. So the leading value is just the value of a random cut. You just cut a value, a graph at random, and you get n squared times p over 4. Each edge is cut with probability 1/2. The max cut deviates by this by n to the 3/2 times a constant that is the same 0.76 that I described before, and this is minus the same constant. This was proved in this paper. And basically, this same algorithm gives a 1 minus epsilon approximation of these factors. So basically, on random graph, the leading factor is trivial. Once you subtract the value of a max cut, this gives you of the trivial cut, this gives you a 1 minus epsilon approximation of opt for these two problems. Okay, for the rest of the talk, I'll describe the formula for the asymptotics, and this is useful to describe this no overlap gap assumption, try to briefly describe the algorithm, and then some conclusion. And we'll cut some corners in the sense that I will not really explain things as in the paper, but slightly simplified. Okay, so the Parisi formula gives you the value of opt, the asymptotic value of opt. It's a beautiful formula. I mean, okay, let me describe it to you. Let gamma be a non-decreasing function from 0, 1 to the non-negative. I'll call curly M the space of some function, such functions, and solve this partial differential equation. This is a partial differential equation in the unknown phi that you can solve backward in time from time equal 1 to time equal 0. You start at time equal 1 from this initial condition, and you propagate the equation backward. You obtain a solution at time equal 0. You plug it in here. This solution depends on gamma, because this coefficient depends on gamma. And now you add this linear function of gamma, and now you get a functional p of gamma, which is a functional over the space of functions. Okay, and the theorem of Talleyrand, okay, this is in a form specific for this case by Haufinger and Chen, but the theorem of Talleyrand says that if I let n goes to infinity, sorry, here I wrote 2 n's, but only one n goes to infinity of the opt, this is equal to the minimum of this functional of gamma. And you evaluate numerically, you can minimize this, it's 0.76. By the way, a beautiful thing about this thing is that here you have a max and here you have a min, is the typical thing you would expect in convex optimization, but this is not a convex problem. So there is some kind of hidden duality that emerges in this problem. Okay, so what is the no overlap gap assumption? Is that if you take this unique minimizer of P of gamma, it's known to be unique because P of gamma is known to be convex, strictly convex, then gamma star, this minimizer, is strictly increasing in 0, 1. Okay, this is a question in analysis. You optimize this functional, and then the optimizer is strictly increasing. On the basis of both physical argument and numerical simulation, numerical solutions of this problem, this is widely believed to be true. If not, you can probably modify this problem to get a problem in which this is true. But this is an open problem to prove this analysis fact. Okay, this analysis fact actually is an interesting interpretation, geometric interpretation. Let me try to describe it. Look at the super level set of this energy function, of this objective function. So everything that is more than 1 minus epsilon of opt. So these are random subset of the hypercube. And then the no-overlap gap corresponds to the following. For any T1 interval T1, T2, or any non-interval T1, T2, you look at, there exist two configurations that are in this super level set, whose scalar product, once normalized, is in the interval T1, T2. Basically, near optima can be at all distances from each other. Morally, this says that near optima forms some kind of connected set. Not really true. I mean, it's much weaker than that, but yeah, it's much weaker than that. You know, all scalar product. So this overlap gap assumption already appeared in the algorithmic literature. For instance, you know, this paper of Gamarnik-Sudan shows that in another model, the existence of overlap gap in some sense implies the failure of some class of local algorithms. But it's a different problem. Okay, now I'll try to describe the algorithm that achieves you know, this theorem, that proves this theorem. These are not necessarily local maxima, are elements of the super level set. Yeah, they can be at all, you know, if you give me an angle, theta, between 0 and pi over 2, there is a pair that is roughly at that angle. Okay? So this is not the same as saying it's connected. Okay, what is the algorithm? Okay, so let me describe before then the algorithm, what is the strategy, which is more important to come up. The strategy is, in one sentence, is take the solution for the optimum asymptotics, the asymptotics of opt, and reverse engineer to get an algorithm. More in detail, you know, the way the proof goes, I'll give you a general class of algorithms that are parameterized by two functions. This class of algorithms are built in such a way that I can analyze them exactly for any choice of these two functions, and then I'll optimize over these two functions. In fact, I'll guess the optimal choice of these two functions. Okay, so the structure of the algorithm is very simple. You have a state that is a vector that is n-dimensional. So you have a real number for each vertex of your graph if you are doing max cut. And then you have iterations, and I'll index iterations in this funny way. Instead of 1 to n or 1 to whatever, m, I'll index iteration as 0, delta, 2 delta, etc., up until 1. This is, I think, the right way to think about it. So I only do 1 over delta iterations. And at each iteration, what I do, I basically compute some function of all the past iterates, multiply by matrix A, and this gives you the new state. Okay? Now, this function is not by itself. I subtract also something that is a memory term that involves all the function up to time t. Now, you might say, okay, this function can be whatever, so you didn't tell me anything, but in reality, things are constrained because this function will be separable. So all the vectors up to time t is really a matrix that is, t over delta times n, or n times t over delta. And what I'm saying is that this function, computes a function row by row of this matrix. So at vertex I looked at the past values only of vertex I and apply some linearity. And okay, and these constants are some constants that are explicitly given. So if you think about it and you forget this term, this is some kind of nonlinear power iteration, general nonlinear power iteration. Okay, so this is very general. So nonlinear power iteration is something that you would do if you wanted to optimize the quadratic form, for instance, on the sphere. Then you would do maximum eigenvector, you do power iteration. Here I'm maximizing it over the hypercube. So it makes sense that I have to do some nonlinearity somewhere, for instance, to avoid that things spill over the hypercube, coordinates become bigger than 1. Of course, the question is how you analyze it and how you choose the functions. Now, I'm not going to describe this in detail, but there are two insights. One insight is that if you construct in the right way this term that you subtract, actually what you subtract is the expectation of the first term given the past. Okay, it doesn't matter, but what happens is that if you construct it in the right way, and if you look at one coordinate of these vectors over time, it forms a Gaussian vector with some covariance. So the coordinates of this vector B, basically, are roughly Gaussian with a certain covariance, and jointly across time. This is the first thing. And the second thing is that the covariance can be computed recursively using the following fact, that basically this map gives an isometry between F and B. The scalar product of B at 2 times, incremented by delta, is the same as the scalar product of F, at time, at delta earlier. This fact is not obvious at all. This fact is kind of magic. It's not obvious at all because these vectors B are correlated with this matrix A. Both facts are not obvious because these two are correlated, but basically what's happening is that this guy is eliminating the effect of all the correlation. So there is a general technology for analyzing this type of algorithm that we started calling approximate message passing. The key insight too is that okay, you gain a lot of simplicity if you constrain your update to be orthogonals. So orthogonal means that in the following sense, that the change between B and B at the next step, I want it to be orthogonal to B at the previous step. So at each step, I move in a direction orthogonal to the past, and then I move to a direction orthogonal to the past, and so on. This is actually something that appeared in a simplest, somewhat simpler problem in a paper, a very nice paper by Eli Ransubach. It's of the spherical spin glass model. There it's very clear why orthogonality works, but if you use it here, it simplifies a lot of operation. And how you enforce orthogonality, well, basically you enforce it recursively. You assume it that holds up to time t minus delta. You use the fact that the projection of the integral of the increment of the previous iterate is equal by this isometry property to the projection of the increment of f of the past iterate. And then if you construct f in this way, you have orthogonality holds by induction. Okay, this is not, this is important, but I don't assume you to be able to follow. But basically what happens is that you construct f in such a way that f is a martingale, and by the isometry property, B turns out to be a martingale as well. All right, this is the overall algorithm, and then you output the sign of this z. So the most complex operation is this one and this n square, so n square over delta, and you choose delta as a function of epsilon. Okay? So you can then, for any choice of this function v and g, you can analyze the cost that you achieve, and this depends on a stochastic process, and then you optimize v and g. Basically, the analysis says the following: solve this one-dimensional stochastic differential equation, compute the stochastic integral, and the asymptotic value of this algorithm is given by this integral. And now you optimize this integral over all functions that are admissible by this theorem, and magic, you obtain Parisi formula. So there is this magic that the dual of the Parisi formula is a stochastic optimal control problem that is really implemented by the algorithm. Okay, so I did something that it's not polite to do in this conference, but I did it anyway. I implemented the thing, right? Yeah, so these are my hi of t. These are basically the variable that I optimize, and you see they follow. These are 5 variables of 1,000 or 10,000 dimensional vectors, and they follow some stochastic process whose limit behavior, limit distribution I described before, and then I did it for various value of n, of the size, and the physics literature says that you should extrapolate like n to the minus 2/3, and if I extrapolate, I get the magic 0.763. So I was pretty happy with this. Okay, so this is of the prototype of a large class of random optimization problem. As was mentioned, there has been 2 papers on in particular this paper of Eli Randa's, a spherical model that is, somehow has some simplification because of the spherical geometry. The talk before gave an example of how statistical physics has been very influential in determining typical properties of random optimization or random constraint satisfaction problem, for instance, satisfiability threshold, value of the optimum, etc. I think now we are starting to see interesting example of algorithms that actually with provable guarantee to achieve those optima, and these are algorithms that you wouldn't have guessed from a standard perspective, and in fact we don't have any, say, classical algorithm that achieves the same. That's all, thanks you. Yeah, yeah.
Can you shed some insight as to why sort of large deviations in the tail of the distribution don't disrupt it?
Well, that is actually not hard because, I mean, think of the optimum as a function of this random variable in the matrix, and then you basically use Lindeberg swapping trick. I don't know if you do in which you replace the same way you prove Lindeberg central limit theorem. You replace each variable by Gaussian progressively, and you bound the difference. So this was done. The first one people who do this is Carmona and Hu, and then we did a more sophisticated version of it with Dembo and Sen a couple of years ago. And so you get that even relatively sparse, for instance, graphs are, controlled by the same kind of asymptotics.
The theorem statement that you had a few slides ago, that doesn't assume the...
Sorry?
The theorem statement that you had maybe in slide 22 or so, that doesn't assume the no overlap property.
Right. So this analysis, okay, here perhaps I'm mixing some, okay, I'm missing some, but you don't assume here overlap properties, so I can get a value for any, even if the overlap gap assumption doesn't hold, and in fact, okay, this analysis should hold also for, should be generalizable to other models. And now the point at which the overlap gap assumption kicks in here is proving that the optimum of this is the same as, and so what happens is that somehow this is an optimal control problem. You can put a Lagrange multiplier for one of the constraints, and this turns to be exactly this function gamma. This function gamma, this is called the Parisi measure, is the Lagrange multiplier. And this fact that it's strictly increasing corresponds to some kind of complementary slackness condition. So it's the fact that, strong duality holds is related to, this not